All right, there we go. So, hello, my name is Addison Branch. I work in the Peer Tutoring Center doing calculus and gen chem. So, let's go ahead and get started going through our review. All right, so the first main section that we're going to have covered on this exam is going to be section 2.1. That one is going to be covering tangent and velocity problems. So, just as a quick review, our tangent line is a line which touches the function at a particular point and has a slope that moves in the same direction of the curve as that point of contact. And a secant line is similar, but that the difference is that will intersect the curve at more than one place. So in this example up here, we have a function that we just have a general function in our red. And if we look, we have our blue line right here. That's going to be our tangent line. We can see it only touches in one point, and we can see how, like, when you get really close to that point it touches, it kind of moves in that same direction. Whereas we have our secant line in green, which is touching at more than one point. So whenever we're using tangent lines and secant line, so when we're looking at this, secant lines can actually be used to approximate the slopes of tangent lines. And the accuracy of the approximation will increase as the points you use and the secant line get closer to where your tangent line is. So for example, if we kind of go back over here, we can see that green line, it looks fairly close. It looks close-ish to the blue line. Which is our tangent line, but so for example, right here where you're picking points 0 and 1 to calculate, whenever and our tangent line is at 0.5. But if we pick something like 0.5 and 0.49, those two, that secant line would be a lot closer to our actual tangent line. So our main secant line formula is just our general slope formula. So it's going to be slope is y1, y2 over x. y2 minus y1 over x2 minus x1. And a type of problem you may see like this is they may ask you to go find the tangent line of a particular function given a point. So for that, you'll go ahead and use your point slope formula, which is going to be your y minus y1 is equal to your slope times your x minus x1. So going off of that, let's move into velocity problems. So velocity is the rate of change of a position. So it's essentially like how fast are you going from point A to point B. Whenever we're talking about velocity, there's actually two different ways we can talk about it. We have average velocity, which is essentially how far did you move in a given time interval, and that gives you kind of an approximation of how fast you were moving during that time. Whereas instantaneous velocity is telling you how fast an object is moving at any particular moment in time. So that's so pretty much the big difference is average velocity is a time interval, instantaneous is like one moment. So for the purposes of this section, when we're talking about velocity, when they ask you to calculate velocity, they're talking about average velocity. Now, when we get later on in the review, you'll have instances of instantaneous, and usually your prof will go ahead and usually they should go ahead and clarify which one they want you to solve for. But when you're solving for average velocity, it'll be pretty much the slope formula again. It'll be your average velocity is equal to your change in position and over your change in time. And instantaneous velocity can also be approximated using average velocity in a similar way that secants can be used to approximate tangents. So with that, let's go ahead and just kind of do a quick example. So this one, we'll go ahead and cut a little bit of this just for time, but in this example, they give us a point and a curve, and they're wanting us to approximate the slope of our secant line to 6 decimal places. For the purposes of this, let's just cut, we're not going to do these pieces because that's just going to be pretty repetitive, but just so you can get used to having actually plug these in. So our first step that we'll need to do, well, actually, they went ahead and gave us our x and y, sometimes they may not give you your y. And so if they don't give you your y, you'll have to solve for that first. But in this case, we have both of our x and y in our point. So now it's having to find these other 2 points. So let's go ahead and solve for both of those. So we'll go ahead and plug this into our function. So we'll say y is equal to 1 over 1.999. Wait, 1 minus. There we go, 1.999. So if we go ahead and calculate that real quick, give me a second to plug that into a calculator. That is going to get us 1 over negative 0.999, which that is going to be approximately, that's going to give us approximately -1. That'll technically 1.001. Let's just do 3 decimal places for this example. And we'll go ahead and do repeat that again with our other piece with that 2.001. So let's do y is equal to 1 over 1 minus 2.001. That's going to be equal to 1 over negative 1.001. And that is going to get us, give me just 1 second, negative 0.999. And for this one, whenever you're trying to use secant lines to approximate your tangent lines, you usually want to try to take 1 point to the right of your original point and 1 point to the left. That way you can just kind of get a good idea of the behavior on both sides and just make sure everything's matching up properly. So now it's time to go ahead and actually calculate our slopes. So of course, our formula for that will be m is equal to y2 minus y1 over x2 minus x1. So we'll do that for both of these. We'll do negative 1.001 minus negative 1 over, that'll be 2 minus, for that one, that was the 1.999. Wait, actually, give me a second. I got that mixed up. All right, right here, yeah, let's go and rewrite our points like this. We're going to do 1.999, negative 1.001. There we go. And let's rewrite it like that down here, 2.001, negative 0.999. All right, so yeah, let's go back to this. We'll do 2 minus 1.999 over negative 1 minus negative 1.001. And that's going to get us 0.001 over 0.001. So that's going to get us 1. We'll repeat that for the second one. We'll do 2.001 minus 2 over negative 0.999 minus negative 1. And that will get us 0.001 over 0.001 again. And that one's just going to be 1. So we can go ahead and see from both of these approximations that, so we went ahead and calculated for part A. For part B, we can see with these approximations, both of those slopes came out to 1, so we can say our m is equal to 1. And for now, just for the purposes of time, let's go ahead and just skip part C for solving for the tangent line. All right, for section 2.2, that is just pretty much teaching you how to define a limit. So your book definition is saying that if f of x is defined, let me see, is everyone muted? All right, yeah, so if f of x is defined, suppose f of x is defined when x is near the number a. So that means that like your function is defined on pretty much some open interval that contains a, but it may not have a. So you may have a small like discontinuity at a. Then we can say the limit as x approaches a of f of x is equal to L. So essentially what this is saying is we may not necessarily be directly looking at a, but we're looking at a bunch of numbers, at all the numbers that get really, really, really close to that a. And we can see from where they are on their graph, that can kind of give us an idea of the behavior of what a is doing. So it's like if we pick a number really, really close to a, we can usually say, okay, that's pretty much a good approximation of f of a. We can also, and then that same logic can apply with the one-sided limits. So essentially what you can do is you can so whenever you're talking about that previous example, they're just talking about in general with both sides of a, but you can also do it one side with just a. So your notation for that, so if you're going from like the negative side or from the left, you'll say like your limit as x approaches a from the left or a from the negative side of f of x equals L. But you're only looking at one side. You're not looking at like anything to the right. And the same logic will apply vice versa whenever you're looking at x approaches a from the positive. You're only looking at everything to the right of a. You're not looking at anything to the left. All right, so this is just a quick conceptual example. So if we're given a graph of f, you can maybe get a graph and they'll tell you to explain each quantity. So for example, if we're looking at this, this example for a, they're telling us, look as x approaches 2 from the negative. So that's going to be like we're going to approach from the left. So we're going to go over here. We can see as we're getting close to 2, that's going to get us close to the point 2, 3. So we can say that that limit is equal to 3. Whereas part B is asking for us to go from the positive, so we'll go ahead and go there. We're going to get really close to the positive side. And we can see that that is going to be at approximately the 0.21. So now they're asking us for our limit as f of x approaches 2. So for your limits, whenever you're both sides have to be equal for the limit to exist. And since these two don't equal each other, then we have to say that the limit doesn't exist because we can't definitively say it's doing this at 0.2 because it changes whether you're going from the left or the right. And we'll go ahead and skip part D, E, and F for right now. If we have time, we may come back to finish some of these examples, but we'll just go ahead and just keep moving. All right, and then sometimes you may have something where your limit approaches infinity. So essentially the way you may have a case to where you may have a limit where as you approach a certain value, it just gets really, really big. So for example, let's say we have this graph that looks like this. As we can see right here that as we get really close to that y-axis, that number is getting increasingly big, is getting really, really large. And in that case, we'll say that our limit is going to approach infinity. And whenever we have a limit that approaches either positive or negative infinity, and it can be either on one side or both sides of that limit. It can be either the right-handed side, the left-handed side, or both. We consider that to be what's called a vertical asymptote, and that's essentially just the definition. A vertical asymptote is whenever your limit approaches positive or negative infinity. All right, and then we have another quick example. Let's just go ahead and just skip and do part E, which is going to be the equations of vertical asymptotes. So whenever we're looking at vertical asymptotes, your equation is always going to start with x equals, because because that'll just be some sort of vertical line that is going to be our asymptote. So now we'll look and see kind of around where any place where our limit appears to be going to positive infinity, negative infinity, or both. So we can see right here with around -3, we have both pieces getting really, both of them are getting really, really large right there. So we can say that that's our first one. We can go ahead, keep going it down our graph. We can see our graph getting really, really negative down here at x equals -1, so we can consider that another one. Now over here at 2 is kind of interesting because we have it going both up. We have it going up from one direction and down from the other. Even though those don't match, that'll still be a vertical asymptote because it's still getting really big or really large. So that'll be our last one for this graph. All right, section 2.3 is going to go ahead and go over our limit laws and how to actually calculate limits. So limit laws, they're pretty simple. They just make our calculations a lot easier. So the main ones that we've learned in this section, we learned our sum law, which means that we can break apart and we can go ahead and break apart an equation into different ones and add them together. Our difference law works the same thing. If you have an equation with the subtraction symbol, you can split that apart into separate limits. Our constant multiplier pretty much says if we have a constant multiplier within that equation we're taking the limit of, we can actually go ahead and just pull that out in front and then multiply the end. Our product rule, which essentially says if they're multiplied, you can split them up, and same thing with our quotient, you can just split them up and solve them separately. There are also a few more limit laws that y'all should know for the exam. So our first one that we have right here is our power rule, which essentially says if we have a function raised to a power, we can actually solve for the limit of that inside function first, and then put that, and then raise that to the other power. We have our constant rule. So essentially, when you think about that, the graph of a constant is literally just going to be a flat line. So it doesn't matter where you are when you take the limit. It's just going to be that same constant value. Limit as x approaches a of x is always going to be equal to a. When you think about that one, it's essentially we just have that y equals x line where you know everything is going to be completely one-to-one. And then number 9, it's pretty similar. We can go ahead and just plug in our value. Same thing with number 10. You can plug that in if you have like an exponential or like a square root equation. And we can also generalize this number 10 out to number 11 to where if we have, which number 11 is also pretty similar to 6. If we have a function raised to a power, we can just pull that out and solve for the limit separately. But the biggest one that you'll use, and this should usually be your first attempt whenever you try to solve for limits, is going to be your direct substitution property, Or essentially you just plug in the thing that you're, plug in your a into your function. All right, and then some other important ones that can help you calculating is direct comparison. So essentially we have one to where if you have a function where you have like a little, where you have two functions that are almost exactly similar, but one may have like a small hole in the graph, but you're trying to find the limit of where that hole is, you can take that other equation that's virtually similar and use that to solve for your limit, and just use direct substitution. We also have this other one right here that says if g is greater than x, if g is greater than f, then the limit of g will have to be greater than f. And that one's pretty much just common sense. If we have one function like this, and we have another one like this, the y value of that pink one is always going to be bigger than the y value of that black one. And the next big one we have is going to be called squeeze theorem. So essentially what that one says is if we have three functions, f, g, and h, where g is bigger than f and h is bigger than g, and if we know that the limits of f and h are the same, then g also has to be that. So if we think about that graphically, if we have our f function that looks something like this, and then we have our g function which looks something like this, and our h function which looks like this, if we for sure know the limits of h and f, and we know that those are equal, then logically g has to be the same as all of those. All right. We have another one, just calculating, another example, just calculating using limits laws. Essentially with that one, we can try our direct substitution first. And when we do that, we're going to get square root of, we're taking the limit as x approaches -4. We're going to get 16 minus plus 9 minus 5 over -4 plus 4, which is going to get us 0 over 0. We can't necessarily solve our function like that, so we're going to have to go ahead and play around with what we have. Whenever you have a square root, usually a good idea to do is to kind of multiply it times something similar. So we can multiply it times x squared plus 9 plus 5. So we'll multiply it times the same thing where the root is, but we'll just flip the middle sign. X squared plus 9 plus 5. All right, so if we take x squared plus 9, if we multiply those two, x squared of x squared plus 9 times square root of x squared plus 9, we will get x squared plus 9. X squared plus 9 times 5 times square root of x squared plus 9 negative 5. Those will cancel, and then we are left with minus 25 over, we can get x plus 4 times the square root of x squared plus 9 plus 5. From here, we can go ahead and try to do a little bit of simplification. We can get x squared minus 16 on top, which that will go, we can factor that to x plus 4, x minus 4 over x plus 4 times the square root of x squared plus 9 plus 5. That x plus 4 will cancel out, and we can try to take the limit one more time. And see if it works this time. So we'll get negative 4 minus 4 on top over that square root of -4 squared plus 9 plus 5. So we'll get -8 over that square, that everything under that root is going to go down to 5 plus 5, -8 over 10, and then that can simplify to -4 over 5. All right, section 2.4, that one's going to be the precise definition of a limit. So essentially for that one, it essentially states that if we know for a fact that the limit as x approaches a of f of x equals L, for every number where epsilon is greater than 0, there is a delta greater than 0 such that 0 is less than the absolute value of x minus a is less than delta, and the absolute value of f of x minus L is less than epsilon. So let's go ahead and actually think about this graphically. Essentially what this is saying is if we have a graph and we have a function and we have our point, and we can say that this is going to be at AL, we can move up or down in some direction along this function. And we can call that difference away from L to be our epsilon. So this can be like L plus epsilon, L minus epsilon. Well, those points are going to correspond down here to our x-axis. So of course, right here in the middle, we have our A, and then right here we have our A plus delta. So delta is essentially how far away from A we moved, and over here we'll have our A minus delta. So that's essentially what that's saying is, so as we move some distance, delta away from A will move some epsilon away from L and vice versa. And that same definition can also be applied to like single-sided limits. The only thing is it will just slightly change the way that your inequalities will be set up, and pretty much all it is just showing like and it's just showing what side of A you're looking at. So for example, that left-handed limit, and if we have like a left-handed limit like that, and we have our function, and we know that this is our A, all we care about is like the delta is like A minus delta. We don't care about A plus delta because all we care about is that left-handed limit. So that's why that inequality gets changed to A minus delta is less than X, which is less than A. We also have the precise definition of an infinite limit. So what that one says is that let f be a function defined on some open interval that contains the number a except maybe a itself. It says that for every positive number m, there is a positive delta such that if 0 is less than x minus a, that's going to be less than delta, so f of x is greater than m. So essentially what that's saying is if we have a limit that's going to infinity, so we'll go ahead and call that point A. And our limit's going to infinity. there will be some point m, right? We'll have some point m, that's going to be a y value, that we can define, and we can say that everything like to the other side of that m, or that's like delta away from a, everything that's like that delta away from a is going to be greater than m until like we hit that spot. And the same thing applies when you're going negative, except you'll say, so like you can go some delta away from A and you'll hit a point, but then everything within that delta space is going to be lower than that n value that you assign. But essentially the proof works almost exactly the same way. So we'll go ahead and try to do a quick example for how to like show the how to do a proof for this, because this could be something that could pop up on your exam. So essentially the first thing we want to do is we're going to go ahead and first create our delta and our epsilon statements. So if we go back to that first section, we have our inequalities that they give us. They say that x minus a is less than delta, and f of x minus L is less than epsilon. And then we have f of x minus L is less than epsilon. So what you're going to do is you're going to go ahead and actually plug in your values that you have from your limit equation. So your a right here we have is going to be our 2. And then our f of x will just be our function. So that would be our x squared plus 2x minus 7 minus our limit, which is that 1, so minus 1. And that's going to be less than our epsilon. So essentially the way that I like to go ahead and approach these problems is go ahead and start with our epsilon. So let's, usually what I like to do is try to kind of recombine and see if you can either simplify or factor anything. So let's go ahead and combine that 7 and 1 to give us our x squared plus 2x minus 8 is less than epsilon. Well, when we look at this, this is actually going to be something that can easily be factored. So we can say that's going to be x plus 4 and x minus 2. So from here, what I also like to think is say, is there anything in this new epsilon statement that looks similar to our delta statement? So we can see we have an x minus 2 here and an x minus 2 here. So what I like to do is try to isolate that x minus 2 by itself to get us the absolute value of x minus 2 is less than epsilon over the absolute value of x minus 4. So we can divide both of them. So now we have this x minus 2 here is less than delta, and x minus 2 is less than epsilon over x plus 4. So from here, we'll make a statement, and we will go, since those inequalities are almost exactly the same, we'll make a statement that says that delta is equal to epsilon over x minus 4. I mean x plus 4. There we go. X plus 4. But now we just have to go ahead and double check and make sure that this statement is accurate. So what we can do is we can take this statement. So we solved it using our, discovered it using our epsilon equation. So what we'll do is we'll plug this statement back into our delta equation. So we'll go ahead and say that now x minus 2 is less than epsilon over x plus 4. I'll multiply both sides times x plus 4, because essentially what we want to do is try to re-isolate our epsilon now that we're back in the delta equation. So x plus 4, x plus 4. So now we're getting x plus 4 times x minus 2 is less than epsilon. We can go ahead and re-expand that back out and see that we have x squared plus 2x minus 8 is less than epsilon. And then we'll get x squared plus 2x minus 7 minus 1 is less than epsilon. So now that we're right back to where we started up here, we can say for sure that that statement is accurate. And essentially what this means is that if we move delta away from some delta away from 2, then we'll be moving, that'll give us like our epsilon statement of like how far that will correspond to like how far that movement is. And we'll go ahead and skip this example for time. All right, so section 2.5 is going to be continuity. So the definition they gave us is that a function is continuous at point A as long as that point exists. So, but there's also, or as long as the limit of that point is the same as where that point is. So essentially what that says is there's 3 criteria to determine whether something is continuous. So that point, f of A, has to be defined. And then the limit as x approaches A does in fact exist. And then that limit has to equal f of A. All right, and then whenever we're talking about continuity, we can also talk about types of discontinuities. So discontinuity is just going to be a place where a function is not continuous. And there's 3 main types of discontinuities. The first one is going to be removable. And essentially what that one is going to look like is if we have a function with a very small hole cut out of it. And those are discontinuous because they don't meet the criteria to where f of A has to, is because f of A, yeah, it's discontinuous because f of A does not exist, so therefore it fails one of the criteria for it to be continuous. Now, for this one, the limits will still exist, but it's just discontinuous there. And you'll usually see these in like a rational function where like a denominator could be canceled out. So like an example you may see would be if you have like x squared minus 4 over x plus 2. Hypothetically, you could think about this as saying we have x plus 2, x minus 2 over x plus 2, and then say that this is equal to x minus 2. Well, your function would look exactly like x minus 2 for that graph. But there would still be a hole at x is equal to -2 because you can't discount that piece in the denominator. So they'll factor out and look almost exactly the same. The only difference is that one would, this one would have a hole in the graph, whereas plain x minus 2 wouldn't. You can also have infinite discontinuities. So essentially that's going to happen whenever your limit at a point approaches positive or negative infinity. So something like this. Though, of course, those are discontinuous because typically in that scenario, your f of a is not going to exist. And technically, your limit wouldn't exist because it would be approaching infinity. And that's, so like infinity would technically be it does not exist. But that would be a vertical isotope right there. And usually that will be seen in a rational function where you can't cancel out a denominator. So like an example like for this would maybe be something like 1 over x. It doesn't matter what you do to that. There's always going to be that whole at x minus 0, and that's going to go to infinity. And usually you'll see that whenever, and usually that'll be when the power of the denominator is bigger than the one in the numerator. Or that's just a generalization. Of course, there may be some exceptions, but just in general. And then lastly, you'll have jump discontinuities, and those will look something like this, to where you have a function, and then it just jumps up at another piece. And that one fails for continuity because even though the point may exist, the limits aren't going to match. And the place where you'll probably see that will be in a piecewise function where they give you something like f of x is equal to like g of x when like x is greater than something, and h of x when x is less than or equal to something, like the ones that look like that. And then we can also have, and we just discussed continuity at a point, but we can also have continuity on an interval. So essentially, f of x can be continuous on an interval as long as f is, it's continuous on an interval when every single point on that interval is continuous. And it's okay, actually, if you have an interval, but it only is defined on one side. So for example, if we have something, so for example, if we have a function that looks like this, and we'll say this point is, we'll call this one, say like this is -1, 0, this one is 1, 0. As long as that limit as x approaches -1 from the positive is good, and that limit as x approaches 1 from the negative is good, we're okay. Because we're just checking the limits that fall within that interval. Because it doesn't matter what's happening out here because that's not part of our interval, as long as like our interval is like that 1 to 1. All right, and then we kind of also have some rules to kind of just help you check with continuity. So essentially it says that if we have two functions that are continuous, if you add them together, the sum will be continuous. If you subtract them, the sum will be continuous. If you put a multiplier out in front, they'll be continuous, like a constant multiplier in front of one of them. If you multiply them both together, they're continuous. And if you divide them, they'll be continuous, but except for the point where that denominator is going to equal to 0, then there would be a discontinuity. And then we also have some kind of generalizations to help us tell when function types are continuous. So polynomials will always have, will be continuous everywhere from -infinity to infinity. Rational functions are going to be continuous. So if we have like a rational function that's going to be function f divided by function g, those are going to be continuous whenever g does not equal 0. When g does equal 0, then there's going to be discontinuity. root functions, remember those are going to be like this. So for those, you just have to double check your domain. So in general, even root functions, those may have limits on their continuity. Those may have limited domains. So you have to check your interval. And in general, odd root functions, those should be those will typically be continuous everywhere, but you still have to just double check what's under that root and just triple check your domains. Trig functions, those depend. So sine and cosine are gonna be continuous everywhere, but the rest of your main ones will have discontinuities. Inverse trig, that's another one where you'll have to check and see. Some of them may be continuous everywhere. Some of them may have discontinuities. It just depends on which ones. Exponentials are typically continuous everywhere, and logarithmics are continuous on their domain. So their domain may not be, won't be from. So their domain will not be from negative infinity to infinity, but where their domain doesn't exist, they should be continuous. And once again, most of those are generalizations. You sometimes still have to just double check and make sure. You may have like different function types put together, so you may have to just double check for each of those, depending on the circumstances. All right. All right, so we have a couple more theorems to use, so that we've also learned in this section. So we have one that says if f is continuous at b and the limit as x approaches a of g equals b, then we can actually put those together. We can actually kind of combine those together to say that the limit as x approaches a of f of g will be the same as f is the limit as x approaches a of g. So essentially what that's essentially saying is if we have a function, so yeah, what's essentially saying is, so we have this function right here, and we know that limit's going to b. And as long as that is continuous, as long as f is continuous at b, so there's no discontinuity, you can just plug that in. You can actually just plug that g function inside of f, because sometimes that makes it easier to solve for the limit. So that will be helpful when you have composite functions. And another one that may be useful for composite functions is this second theorem down here. So it says if g is continuous at a and f is continuous at g of a, then the composite function is going to be continuous at a. All right, so we have a quick example. So this one says, for this one, we'll just say find the number. We'll just only do the part to say find the numbers at which f is discontinuous. So when you're given a piecewise function like this, the first thing you want to do is you want to check your domain and make sure that everything's going to fall within your domain. So this one, so this interval falls within our domain. This interval, x squared, has an infinite domain, so that one's good. X has an infinite domain, which is good, so that one's good. 1 over x does not exist at 0, but that's not within our interval, so we're okay. So we've got that first check. The next thing we want to do is check to see if all of our y values match up at like these intersections. So the first thing we'll check is at x equals -1. So what we'll want to go ahead and do is we'll actually go ahead. So we know that the function doesn't exist at x equals x is less than -1. I mean when x is greater than -1 for x squared. So we'll take our limit as x approaches -1 from the negative, since that's within our interval of x squared, and that's going to go ahead and equal 1. then -1 does exist for this f of x equals x. So when f of x equals x, f of 1 is going to equal 1. So we're good at that x equals -1. So now we need to check our next gap, which is going to be at x equals 1. So we'll need to go ahead and take our limit as x approaches 1 from the negative of x. And that's going to go ahead and equal 1. Oh, wait, I just realized I had an error in my math. There we go. That's a -1. We are checking -1, so actually that one's not good. 1 does not equal -1, so there actually is a discontinuity at x equals -1. All right, going back to that one, limit as x approaches 1 from the negative of x is 1, and then we'll do f of x is 1 over x is equal to, we'll go ahead and plug in our 1 there, since that does fall within our interval. That's 1, so these two equal each other, so that one's continuous, but we still have that discontinuity at x equals -1. All right, the last thing we got from this section is going to be the intermediate value theorem. So what this one is saying, so if we know that f is continuous on an interval from a to b, so we'll say that this is a and this is b, and then n can be any number between f of a and f of b. And as long as f of a does not equal f of b, then there has to be a number somewhere to where f of c equals n. And so this theorem is pretty much just basic logic. If we know that there's no gaps within that function, and we know that f of a does not equal f of b, then we know that there has to be some, we can essentially say that there has to be a corresponding x value to any y value within this section between that f of a and f of b range. All right, I'm going to go ahead and skip the example for that one for right now. All right, we have section 2.6, which is going to be limits at infinity. So essentially what this one says, you may run into situations to where if you take your limit as x approaches infinity of a function, you may actually get a finite number. And essentially what that means is no matter how big you make your x value, it's going to approach that L. And whenever that actually happens, whether you're going to positive or negative infinity, that's actually going to be called a horizontal asymptote. So if you go either get very, very big in the x direction or very, very negative in the x direction, you may, if you have a horizontal asymptote, it'll always approach like some finite number. But of course, not all limits going to infinity are going to have a horizontal asymptote. You just have to kind of look at your function. All right. Let me think. How many more slides? We may come back to that one. Essentially, the main strategy for this one when you're solving for limits at infinity is you want to go ahead and divide everything by like the biggest like x power. So for here we have x to the 3. So we'll want to divide everything by x to the 3. So we'll take like 4x cubed over x to the 3 plus 6x squared over x cubed minus 2 over x cubed over 2x cubed over x cubed minus 4x over x cubed plus 5 over x cubed, and then you'll find your limit as x approaches infinity from that. And the main strategy you'll need to know is that if your limit as x approaches infinity of like some constant over x, or essentially if you'll get like infinity in the bottom, that's going to equal 0. But that's essentially the main strategy you'll use to solve for problems like that. All right, section 2.7, we have derivatives and rates of change. So this takes us back to, this is connected to that very first section we talked about. So earlier we said our tangent line could be approximated using a secant line. But now we can actually go ahead and solve for that. We can say that our tangent line at some point A is or the slope of that is equal to the limit as x approaches A of f of x minus f of A over x minus A. And this can also be rewritten to say our limit as h approaches 0 of f of A plus h minus f of A over h. So essentially, these kind of mean the same thing, they're just written a little differently. This first one, graphically, what it's saying is if we have our point A f of A, we can essentially pick a point. We want to pick a point as close to A as we possibly can. So that's where that limit as x approaches A of f of x comes in, because we're just trying to pick a point that's very, very close. So we're approaching A on our f of x. Whereas in down here, what this is saying is, this is just the same thing, just rewritten. So we're saying that we're starting from our A f of A. But they're saying we're moving like virtually 0 away from A. We're going to move like a few units, so 0 units away from A. But they're essentially the same thing, just written in different ways. The same theory can be applied whenever we start talking about velocity as well. So earlier we said velocity is going to be your change in position over change in time. So we can actually take that and use that to find instantaneous velocity. So so what we're doing is we're saying as our time time interval is approaching 0, we'll say that that's how we'll take our limit as our time interval approaches 0. So that's going to be our new formula. So our limit as h approaches 0 of f of A plus h minus f of A over h is going to be our new velocity formula whenever we're talking about instantaneous. And then this can be applied more generally to say the derivative of any function f at number A. Well, the derivative of that point will be the limit as h approaches 0 of f of A plus h minus f of A over h. And that can also be rewritten in the same way as that tangent line formula was, where we can do f of x minus f of A over x minus A. So technically, actually, the definition of derivative is actually going to be just a rate of change. So when we're taking the derivative at a point, we're looking at the instantaneous rate of change at that point. So just in general, when you think derivative, think rate of change. Well, will come back to this one. Let me go ahead and check and see if I have another example like this one. All right, we'll go and skip that one because the process will be very similar whenever we actually do the one where we apply it to a full function. So section 2.8 is going to be the derivative as a function. So 2.7 was just looking at derivatives at specific points, whereas 2.8 is looking at derivatives of full functions. So essentially the derivative as a function will be, the limit definition will be the limit as h approaches 0 of f of x plus h minus f of x over h. So that will give you your rate of change of the entire of your entire initial function. And you can go ahead and plug in any point into that, and it will give you the rate of change of what that particular point was in the previous one. So just some other details to know about derivatives. So there's actually different ways that they, different notations you can write a derivative. So they can be written as f prime of x, y prime, dy over dx, df over dx, or d over dx of f of x. Those essentially all mean derivatives. And this one in particular is what's called a derivative operator. So whenever that's written in front of a function, that essentially means take the derivative of that function. Now, f of x is going to be, and then whenever we use the phrase differentiable, that essentially means like a function is differentiable whenever you can take, whenever the derivative of that exists. And that can apply to either a point or an interval. Another good thing to know is that if f of x is differentiable, then it has to be continuous. And there's going to be a few instances where f of x may not be differentiable. So the first one is going to be a corner. So whenever you have something like this, where you have a really, really sharp point, you can't do, your function will not be differentiable at that point. It can be everywhere else, but not that particular corner. Same thing goes if you have any discontinuities. So it doesn't matter if they're jump, removable, or infinite. Any discontinuities, it can't be differentiable. And the other one we'll do is whenever you have vertical tangent lines. So whenever you have something like this. So yeah, let's say you have, well, that's, let's say we have something like this and we have a vertical tangent line somewhere. That point with the vertical tangent line wouldn't be differentiable. And when we're talking about derivatives, you can also have higher order derivatives. So whenever we take the derivative of a derivative, that's going to be called our second derivative. And sometimes they may give you an applied physics problem. So whenever you see something like that, the second derivative is associated with acceleration. And then they could also ask you to find the third derivative. So that's just going to be your derivative of your second derivative. And I personally have never really seen give very many examples, but in case it comes up, the application for physics would be referred to as a jerk. So, excuse me. So in conclusion, like if we're talking derivatives, like with physics, just a good thing to know is that your initial function is going to be your position. F prime will be your velocity. And then that'll bring you to your second derivative, which is acceleration, and then third, which is your jerk. So now we're going to go ahead and work on taking the derivative of a function, but we're going to use like our limit definition of a derivative. So our limit definition of a derivative is going to be the limit as h approaches 0 of f of x plus h minus f of x over h. So we'll go ahead and plug in our function into that formula, and then we'll get the limit as h approaches 0 of 3 times x plus h. So yeah, everywhere we'll see an x, we'll plug in x plus h minus 8 minus 3x minus 8 all over h. All right, we can go ahead and expand that out, and we can go ahead and get 3x plus 3h minus 8 minus 3x. Yeah, if we go ahead and distribute this negative, we're going to get minus 3x plus 8 all over h. We'll see if we can clean this up a little more. So we can go ahead and see those 3x's will cancel out. And those 8's are going to cancel out. So then we're just left with our limit as h approaches 0 of 3h over h. And those h's will cancel out. So now we're just left with our limit as h approaches 0 of 3, which will just be 3. All right, so now we can go ahead and move on to chapter 3, which is going to be how to actually take derivatives without having to use the limit definition. So section 3.1 covers derivatives of polynomials and exponential functions. So the main rules that we learned in this one were that if you take the derivative of a constant number, that's going to be equal to 0. If you take your derivative of x raised to some power, what you're going to do is you're going to bring that power down in front, and then you're going to subtract 1 off from that power. We learned that the derivative of e to the x is going to be e to the x. We also learned for this one, if we have a constant times like a function, and they're wanting us to take the derivative of the full thing, we can just pull the constant out in front. And we also learned that if we're taking the sum or difference of two functions and we're trying to derive, when we're taking the derivative, we can split them up and treat them as two separate derivatives. And just one quick thing that I want to mention right here, because I know this can get some, I have seen people get confused on this before. Whenever we're talking about that e, so e by itself is actually equal to a number. So that's approximately 2.72. So if you see e to like any constant number, that is going to be just a constant. E to the x, now e to the x, because that x variable is up there, that's going to be an actual function. So just keep in mind not to go ahead and get those confused whenever you're taking a derivative. So like derivative of e to the x is e to the x. Derivative of e squared would just be 0. All right, so for this one, we'll just we'll go ahead and just show some quick ones with these rules. So for the first one, we have y equals 2 to the 40th. So with that one, so We have 2 as a constant raised to another constant, so that one is actually just going to be, so when we take the derivative of a constant, that's just 0. For the second one, we have square root of x minus x. Whenever you have a root like this, I find it really helpful to go ahead and actually turn that into a power rule. So, for example, this is a square root. So we can turn that into x to the 1/2 minus x, just because that makes it a little easier to see how to do the power rule. So when we take the derivative, we'll go ahead and bring down each one. So for that first part, we'll go ahead and bring down that 1/2 x, and then 1/2 minus 1 is going to be negative 1/2 minus, and then we're going to have our minus, which will stay out there, and then the derivative of x, it will just be 1. All right, and then for this last one, we have derivative, they're wanting us to find the derivative of e to the x minus x to the e. So e to the x, that one is just, that derivative will just go down to e to the x. Now let's look at x to the e. So if we remember, e by itself is just a constant. So we can actually treat this as a power rule. We can go ahead and bring down that e, x to the e minus 1. And then those were subtracted, so this will actually be our final derivative for that third one. All right, section 3.2, we went ahead and covered product and quotient rules. So essentially, as long as both of if you have 2 functions multiplied, as long as they're both differentiable, then your rule will be, you'll have your first times the derivative of the second. So if we're going to rewrite this in prime format, it'll be your first times derivative of your second plus your second times the derivative of your first. And for this one, it doesn't matter which one you assign to be your f and which one you assign to be your g. Like you should be getting the same answer either way. All right, and then for quotient rule, if we have f divided by g and we want the derivative, we'll go ahead and do the bottom times the derivative of the top minus the top times the derivative of your bottom all over the bottom one squared. So some quick examples for those. This first one, we're going to go ahead and use our, we have this function, this 3x squared minus 5x, and then we have this e to the x. So we have 2 functions multiplied times each other. So for this one, we can go ahead and say that our f function, we can call that one our 3x squared minus 5x. G function is going to be our e to the x. And sometimes a helpful thing to do with your product and quotient rules is to make a little chart saying what your f and g, to have your f, your g, your f prime, and your g prime. So derivative of 3x squared, that one's going to bring down the 2, so be 6 times x to the 2 minus 1, so just 1, minus derivative of 5x is 5, and your derivative of e to the x is just e to the x. So for that first one, we'll be getting, we have your first times the derivative of your second minus your second times the derivative of your first, and that will be our final answer. If you want to try to expand that out and simplify and see if anything simplifies, you can. But just in general, for showing the rule, that's we could hypothetically stop there. All right. So now for our quotient rule, we have our two rules. We can say our f is equal to x. Our g is e to the x. Then we'll have our f prime is 1, and our g prime is e to the x. So that one will be your the bottom one times the derivative of the top one minus the top times the derivative of the bottom all over the bottom one squared. And that's how you would take the derivative for that one. All right, so derivatives for trig functions. The big thing to do for this one is just memorize this chart. So derivative of sine x is cosine of x, and derivative of cosine is negative sine. Tangent is derivative of tangent is secant squared, and derivative of derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant tangent, and derivative of cotangent is negative cosecant cotangent. An easy way how to memorize these is that try to remember that sine and cosine are a pair because those are together. Tangent and secant are a pair, and then cosecant and cotangent are a pair. And you can also remember this because the derivatives for tangent and cotangent have very similar structures, as do the derivatives for cosecant and secant. So just remember their pairs and their structures, and that'll kind of help you memorize. And I find that to be pretty helpful for memorizing them. All right, so this one we'll do a quick derivative for trig functions just so we can get used to using them. So this one we have secant times tangent. So this one would have, so since we have two different functions, this will multiply, that'll be a product rule. So we can go ahead and say our f is secant, our g is tangent, our f prime, derivative of secant is secant tangent, and derivative of g is secant squared. So we'll do our f times our g prime, so secant times secant squared plus our g times our f prime, so our tangent times secant tangent. We could probably clean this up a little bit if we wanted to and combine those secants to get a secant cubed. Plus, and then we can combine those tangents to get a secant of x times tangent squared of x. And that would be our final answer. All right, and the last piece covered was our chain rule. So, and that one is essentially when you have, this one's used when we have a composite function, so a function inside of another one. So essentially what you'll do is you'll take the derivative of your outside function, but then leave the inside the same and multiply times the derivative of the inside. And then I don't 100% know if y'all learned this rule yet or not for when you have an exponential that's not e, but essentially if y'all have already covered it, that one, if you have any exponential that's not b, that's not e. That one will essentially you'll do is you'll leave that exponential part the same and multiply it times the natural log of whatever your base was. And then going back to your regular chain rule though, another way that you can think of it is this one, which is whenever you have a substitution method. What you can do when you have your chain rule, you can use something called the substitution method, to where if you have f of g of x, what you can do is you can assign g of x to be u. So where now you have f of u, and then when you take the derivative of that, that one will end up being the derivative of f prime. That'll be the derivative of f, but that u will stay in there, times u prime. And then what this will end up doing is that will turn into f prime of g of x when you undo your substitution, times g prime of x. So last thing we have, let's go ahead and do a couple quick examples with chain rule. So for this first one, we have y equals cosine of x squared. So what we can do is we can say that we have our inside function, which is our x squared, and we have our outside function, which is our cosine. So what we'll do is we can go ahead and start off by taking the derivative of our outside function, which is the cosine. So the derivative of cosine is negative sine. And then we'll leave the inside part the same. And then we'll multiply it times the derivative of that inside part, which is going to be, so the derivative of x squared, which is 2x. So that will be negative 2x sine of x squared. And then this example we have is going to be cosine squared of x. So whenever you have this squared right next to the cosine, remember that essentially means that we have cosine of x squared, so you can move it completely to the outside. So whenever we have this, we can see, we can think of our inside function as being the cosine of x, and the outside function as being the squared. So we'll start by taking the derivative of the outside, which will be that squared part. So we'll move that 2 down. And then that will turn into just that 1 power, and we'll leave the inside the same. And we'll do that times the derivative of that inside. So that would be negative sine. So our final answer for this one would be negative 2 cosine of x sine of x. All right, so that is all I have prepared for the lecture portion. I want to be able to give you some time to take a quick little break before we reconvene and do breakout rooms with practice problems.
So we've got practice problems for each of the different sections that Addison talked about. And the first one is about tangent of velocity. So we start with, let's see if this, yeah, okay. So we start with a ball that's thrown at, this is a bit slow. I guess I'll just write slower. At 40 feet per second. And we're also given an equation for its height in feet. t seconds later. So height, okay, this, yeah, height t seconds later is given by the equation y equals 40t, which corresponds to the velocity, minus 16t squared, which actually corresponds to gravity. You don't need to specifically know that, but that's just like something interesting. And they're asking us to find the average velocity for the time period beginning when t equals 2. So when they ask you velocity average beginning um, at t equals 2, what they're saying is they're saying that you plug in a value of t equals 2 plus 2 plus like some time, which would be like that time would be in the form of 0.5 seconds, or I'm going to see if there's a different way I could go about this, because this is um, let's try this. Can I write on this? That's probably not as good. I don't know why the sharing application screen doesn't work. I guess I'll just continue with the whiteboard. Essentially, we've got our y equals 40t minus 16t squared. And if you're asked to find the average velocity given on a time period, so the average velocity on a time period, what you need to do is you just need to plug in different values, and then you need to use the equation. You need to use the equation y2 minus y1 over x2 minus x1. So Addison mentioned earlier that that slope or derivative or velocity are kind of around the same thing. Yeah, the sharing application worked, but the drawing system was the same as yeah, the drawing system was like the same as, it's not sharing my screen, right? Yeah, it's only showing just like that. So yeah. Okay, so anyways, back to the, sorry about the slow start. Um, so this is our equation, and essentially if they're asking you to find average velocity, what you need to do is you need to figure out y of, so average velocity on period t equals 2, like some seconds. And essentially, if they're asking like different parts of like 0.5 seconds or 0.1, what you really need to do is just figure out y at that point. I don't know why I can't do decimals. Yeah, so y at that point. So if it's asking 0.5 seconds, then you would say y of 2 plus 0.5. Or if they're asking for 0.05 seconds, then they would say y plus 0.05. This really isn't just, it's really not letting me write decimals. Yeah, that's kind of annoying. So if you plug in these values for y, so the first one is y at 2.5. these decimals. Okay. Y of 2.5 would give you, so at some point you could do some of these by hand, but at some point you would probably need to use a calculator, especially for like 2.05. And this one would give, mm, yeah, I think it gives 0. So this gives 0, and the thing is that you're trying to find it on a time period. So what you do is you say y of 2.5 minus y of 2 over 2.5 minus 2. And you do the same thing for if they ask for, so if they ask for, actually, yeah, I think I will share the screen or the file because that'll make it easier. Um, Please don't scroll left or right between the slides. I'm just gonna try to do it this way. Um, but yeah, so this is the problem here, and essentially, like, okay, I guess I'll just continue with the whiteboard. Um, yeah, but yeah, so if you follow through with that problem, essentially what you'll be doing is you'll be getting a bunch of different steps. I can, yeah, okay. That somebody linked the folder. Um, Essentially, when you plug these in, um, you'll just get different slopes. And ideally, if you're going 0. What is this? 2.5 minus 2, and then this is equal to negative 32 feet per second. And as you're plugging in each one, so it would be good to get practice into these. I Sorry, I can't share my applications, which is really weird. So otherwise I would have done that. But essentially, this is what you would be doing. And as you plug in different values for y, and then you plug in, so you plug in like the new values for y, you really only need to evaluate this one once. So in this case, y of 2 is equal to 16. And see that from if you plug in 40 times 2 and then minus 16 times 2 squared, and that gives 80 minus 64, and that gives 16. And that's a terrible 80. So essentially that gives these give us different slopes for, or average velocities for 0.05 seconds after and sorry, not 0.05, 0.5 seconds and 0.1 second. And you would do that also for y of 2.05 minus y of 2 over 0.05. Why can't I do decimals? Minus 2. And that kind of continues, and eventually you'll get some sort of number that corresponds to, so let me just clear this board. So if I show you what happens with each of the different values, you would essentially have, so we label the change in time as delta. So delta t, and this corresponds to 0.5, 0.1, 0.05, and 0.01. And then as you're, actually I'll just write these out as well. Really doesn't want me writing decimals. So these are essentially, if you could kind of just assume that there are decimals there, I'm just going to write small circles, and then hopefully that should be fine. But these are the different points, and you can notice that the change in the velocity as you get smaller and smaller numbers approaches us like around like -24. So you could say that the velocity at t equals 2 is approximately -24 feet per second. So I couldn't really write the because like this isn't really going so well with the writing stuff out, but essentially the question is asking you to find the average velocity at specific changes in time. So this is 2 plus, 2 plus, 2 plus, 2 plus. Yeah, you sort of do the limit manually, but it's not quite a limit because you're not um, yeah, it's not quite a limit, but in a sense it's very similar to a limit. The definition of derivative actually does use a limit, so that's just something to keep in mind. Um, yeah, so essentially this is what like is going on. You're calculating the average velocity. Um, so if we graph this out, you're essentially like let's say at t equals 2, or let's say at t equals 2, it's like here. So what you're doing is you're graphing a secant line like maybe like here, and then you're going like here, and then you're going here, and then eventually like you're approaching something at like -24 feet per second. And like the most off one would be the 0.5, and then the 0.1, and then like the 0.05, and so on. So that's what that problem was going on. These problems would essentially just, you would essentially, your main idea is doing the y of t plus delta t minus y of t over essentially delta t plus delta t minus t, if that makes sense. Um, so that's that problem. And then I'm just going to move on to the limits. That might be easier to write at least. And so the limits are, these are like limit problems, so you'll just practice doing these, and you're not allowed to use L'Hopital's rule. So the first question is the limit as x approaches 4 of x squared plus 3x over x squared minus x minus 12. And the first thing that I do, especially when I see polynomials, is I try to factor this. And if you factor it out, then you'll get x minus 4 and x plus 3. And if you notice, you can also factor this one out. You can factor out an x on both sides, and you can see that there's an x times x plus 3. And if you notice that these two are the same, when you write it out like as a fraction, you can see x minus 4, x plus 3, and these cancel out, and that gives you x over x minus 4. So this limit is actually equivalent to, so this original limit is equivalent to the limit as x approaches 4 of x over x minus 4. And that's equal to infinity, because as the bottom approaches 0, this whole function will approach, I can also just write this out. So this will approach 4 over like some very small number. And what that'll end up doing is that that'll just make this overall fraction just approach infinity. So like, for example, like 4 over 10 is 0.4, and then like 4 over 1 is 4, and then 4 over 0 point, or sorry, yeah, 4 over 10 is 0.4, and then 4 over 1 is 4, and 4 over 0.1 is like 40. So you can see that as you decrease the number, as it gets closer to 0, then the number itself approaches a really big number. Let me look at the chat real quick to see if there are any questions. So if we had 2 points that were equidistant from a point, would we find the instantaneous velocity just by finding the average those 2 points y values? So how that works is if you have, so if you had some velocity or so this is height, and if you had some velocity that you're trying to find, if you do 2 points that are equidistant, you can get something close to the velocity, but you want these points to get as close as possible to like whatever you're trying to find the instantaneous velocity for. So like the difference between 2 and 2.5 is a lot larger than the difference between 2 and 2.001 or like 0001. So the closer together the points are, the better it is for the instantaneous velocity. And how do we know if it's infinite, positive infinity or negative infinity? Essentially, at least if you're doing a regular limit and you're approaching 0, it's kind of technically um, neither. It actually does not exist. It could be plus or minus infinity. Like yeah. So because it's negative infinity and positive infinity from both sides, it's not really. If you ever get infinity, it's technically does not exist, but they want you to see the math. They want to see the math that you wrote out to confirm. And how do we find part B on number 1? So part B on number 1 was estimate the velocity, and I wrote it here, but essentially you would see a pattern of as the delta t gets smaller and smaller. What was it? It was 0.01. Yeah, you would just estimate. So the question is asking estimate the instantaneous velocity. Um, yeah, so it's just that question. It's not like precise, but you'll see a pattern as you do the problem, as you evaluate each average velocity. So the next limit problem is the limit as x approaches 2 of x squared minus 4x plus 4 over x squared, x to the fourth, sorry, over x to the fourth minus 3x squared minus 4. And again, the first thing I do is try to factor things out. And don't be scared by an x to the fourth in the exponent, because this is really, it's almost the same thing. So if I factor this out, you'll see that it's almost the same thing as regular factoring, because this is almost, it's not the same thing, but like when you factor it, it gives the same feel as this, as x squared minus 3x minus 4. But instead of x squared, it's x to the fourth. So this is our factoring of this one. And then notice how this is a difference of perfect squares. So you could actually factor this even further to x plus 2 and x minus 2. And then we also factor the top to get x plus 2, or sorry, x minus 2. X minus 2 times x minus 2. And then, as usual, we would see which ones cancel. So what we would do is we write this out in a limit. I'm going to change the color so it's not, actually, I don't like that color. Yeah, Akshan, you're right. That would be negative 24. But yeah, so for this limit problem, we rewrite everything and we get x minus 2 on the numerator. And then the denominator would be what we factored out. It would be x plus 2, x minus 2, and then x squared plus 1. And if you cancel out the x minus 2's, you can notice that the denominator no longer has something that causes a 0, because x minus 2 at 2 is actually 2 minus 2, which is 0. And so now that those cancel out, you can actually evaluate this limit. But notice that the numerator has another x minus 2, which means that the top will actually go to 0 while the bottom doesn't go to 0 at all. So we'll have 0 over, and I'll just write out the actual things, but 0 over 2 plus 2, which is 4, and 2 squared plus 1, which is 5. And that would give, yeah, it would give 0. So 0 over 20, but yeah. And the next problem is another limit problem. These ones are a little bit trickier. You just have to understand how conjugates of for the first one with the yeah. So for those of you watching the recording, I'm just answering some questions on the side. For the yeah, so for the previous problem with the 4 over 0, where you get like negative infinity on the left and positive infinity on the right, it would just be does not exist. So you would write DNE um, because it's DNE if the left and right coincide differently. So um, that's how that one works. And then can you go over how you factored the x to the fourth minus 3x squared? Okay, yeah. So if you're a little bit confused about how I factored x to the fourth minus 3x squared minus 4, um, so what I usually do is I kind of just like, you could actually just substitute like a y equals x squared. So y equals x squared. And then that means that y squared equals x to the fourth, right? So then you would do y squared minus 3y minus 4. And then you would just figure out which factors would work to factor it out. So I kind of just like chunk it out. So you should know how to factor that fairly easily. Yeah. Um, and I think I answered all the questions. Yeah. So I'm going to continue with the next limit problem. This is part of the limits and limit laws stuff. So the next limit problem is the limit as h approaches 0 of the square root of 9 plus h minus 3 over h. And notice how that 3 is actually not inside that square root. And the first thing that you do whenever you see a square root is try to multiply by the conjugate. And if you don't remember what the conjugate is, it is you flip the sign of the thing that is outside the square root. Or, yeah, yeah, so you flip the sign of the thing that's outside the square root. So this sign flips, or if you had, say, 3 minus square root of x, then it would be 3 plus square root of x. So you essentially flip this sign, whatever like the addition or subtraction of the square root and the other number is. And if we continue this, so notice how when we multiply these on top and bottom, this is still equivalent to 1. This factor that we're multiplying by is 1. So we're really just manipulating the equation to get something. Yeah, it's the conjugate. Conjugate. And if you continue multiplying these out, you would get, so this is a product of differences. And so you would get square root of 9 plus h squared minus 3 squared over h times square root of 9 plus h plus 3. And then that top would give 9 plus h minus 9 over h times the square root of 9 plus h plus 3. And then that gives h over h times the square root of 9 plus h. Whoops. Where is an eraser? Nine plus h plus 3. And these h's cancel to give you the limit as h is 0 of 1 over the square root of 9 plus h plus 3. And then that gives 1 over the square root of 9 plus 3 because h is 0, right? And that gives 1 over 3 plus 3, which is 1/6. And that's our final answer for this one. And if you have no questions, I will continue to the next problem, which is our delta epsilon stuff. So the first problem will be looking at a graph, and then the second problem will be evaluating like the actual definition of the limit. So the first problem starts with a graph. So we see x, y, and then let's say 1.2 here, if we can get a decimal here, 1, 0.8. I don't think I'll ever get a decimal here. And the other one, so this is 0 here, and then this will be 0.7, and then this will be 1, and then 1.1. And then what we'll do here is this graph will have some sort of bound. Not exactly a bound, but it's like adjacent lines to show like where the point is on the graph. And then what we're trying to do is show that the limit is within some area or some region of this graph. So our graph is the blue line here. And they give us the statement, if absolute value of x minus 1 is less than delta, then absolute value of f of x minus 1 is less than 0.2. And what you do for this problem is you essentially look at, so there's two possible deltas. There's this one and there's this one. Because delta is essentially the difference between 1 and where you are on the x. So it could be like here or here or here or here. And what you're trying to do is you're trying to figure out the delta that will fit within the bounds. So if we do 1.1 minus 1, that gives 0.1. And then if we do 1 minus 0.7, this gives 0.3. And this one is the smaller one, so we actually choose this for the delta. And you can see that because if you choose 0.3 as delta, then this side would actually be ranging from 1 to 1.3. And this would actually be outside our limit definition, which is not what we want. So if you had it as 0.1, then it would be between here and maybe like about like here. And so then it would be within our bounds, which is exactly what we want. So at least with this, if they're asking about, where did the thing go? Okay. Yeah, if they're asking about delta, then that's essentially what you were supposed to do. And if they're asking about epsilon, then you would have to essentially do the same thing, but on the y-axis instead of the x-axis. The next question is asking about proving the statement, so proving a certain statement using the epsilon delta definition. So in our case, our question is limit as x approaches 1 of 2 plus 4x over 3 equals 2. So we want to prove this limit. And what you start with is you start with a statement. So you start with a statement if you would find the smallest difference on the y-axis. So if absolute value of x minus 1 is less than delta, so we get our 1 from here, and we do if x minus 1 is less than delta, then the absolute value of 2 plus 4x over 3 minus 2 is less than epsilon. So again, we get our equation from this, and we get our limit from here. And if you recall, this is actually the same statement as x minus, I think we use a, and this is f of x minus L is less than epsilon. So that's what that is. And what you do with this is you take this epsilon equation and you try to break it down. And if you break it down, you kind of end up with, so first you would like combine like fractions. So you would turn this into 6 over 3, because 6 over 3 is 2. And you would get 2 plus 4x minus 6 all over 3 is less than epsilon. And then if you simplify that further, you would get 4x minus 4 over 3 is less than epsilon. And then again, if you simplify that further, then you would get 4 thirds x minus 4 thirds is less than epsilon. And I'm going to clear the board, but I'll rewrite it. So you have 4 thirds x minus 4 thirds is less than epsilon. So if you have 4 thirds x minus 4 thirds, again, we want this to look similar to our equation for the delta. So we want our original epsilon equation to approach something similar to our delta equation. And so in order to do that, what you need to do is you can actually factor out this 4 thirds, and then you get that, which looks really similar, but the last thing that you need to do is move this 4 thirds to the other side, in which case you get 3 epsilon over 4. And that, we equate that to delta. And after we found this delta correspondence, then what you do is you take your original delta equation, and then you substitute this in. And what you do is you get x minus 1 is less than 3/4 epsilon. And you kind of just do the same thing in reverse order to get it back into what you were doing. So I'm going to clear the board real quick so I have more room, but I'll rewrite this. So we have x minus 1 is less than delta, but we already said that we already said that delta is equal to 3/4 epsilon. So this is less than 3/4 epsilon. And then we move this 3/4 back to the other side. And then so then we put it inside the absolute value because that's an okay operation to do. And then we would put this into the fraction form because because the original equation was f of x equals 2 plus 4x over 3. So we want it kind of in a fraction form. So we would get 4x minus 4 over 3. Now this is almost there. What we need to do is we want a 2 here. So one trick that I like to do is I would go like this. I would go absolute value of 2 plus 4x minus 2, because now these 2's kind of cancel. So by adding a 2 and subtracting a 2, you get a 0, which is kind of nice. So it's still equivalent to our original equation. And then, so if you notice the difference between what I wrote before and this one, you have a 2 and a negative 2. And this 2 plus 4x over 3 is very similar to our f of x. And then you would get 2 plus 4x over 3 minus 6 over 3. So I kind of did multiple operations in the same step, but it's the 2 and the 4 combined together to get a negative 6, and then I kind of separated the fractions. And that gives us 2 plus 4x over 3 minus 2 is less than epsilon. And now that we showed that both equations are equivalent, it kind of confirms that our statement about the epsilon delta definition is true. And so the next problem is finding continuity or discontinuity. And in the case of this problem, this is asking about discontinuity. And they give us an equation f of x equals, it's a piecewise, so 2 to the x for x is less than or equal to 1, and then 3 minus x for x for 1 is less than x is less than or equal to 4, and then square root of x for x is greater than 4. And so what I like to do is kind of just rewrite it in a way that's like easier for me, at least a little bit visually. And I would go less than or equal to here, and then this is less than or equal to here. And I guess actually it would be better to write it here. And what this does is it tells you that the function is defined on the left side for both at x equals 4 and at x equals 1. And then what you do is you first check the continuity of overall functions. So 2 to the x is continuous for all x. So it's actually, yeah, so it's continuous for all x. And 3 minus x is also continuous for all x. But square root of x is only continuous for x is greater than 0. So if x is any negative number, then it won't exist, or it'll be imaginary. And fortunately for us, f of x is only defined for x is greater than 4. So we actually don't have to worry about this discontinuity because x is greater than 4, which is, of course, greater than 0. And so the other thing that you have to check is you have to check the intersections between these. So when 2 to the x, so we need to see if 2 to the equals 3 minus x at x equals 1. And we also need to see if 3 minus x equals square root of x at x equals 4. So I kind of see it this way. It's like this and then this. And if you plug in x equals 1 into this equation, then you get 2 to the 1 equals 3 minus 1. So 2 equals 2. That actually checks out. So that's continuous. But if you plug in x equals 4, you get 3 minus 4 equals square root of 4. And that's negative 1 equals 2, which isn't true. So there's a discontinuity at x equals 4. And that's actually the only discontinuity for that problem specifically. So the next problem is talking about intermediate value theorem. And when it comes to the intermediate value theorem, what you first need to do is do checks. So let me first write the question. So use IVT to show use the IVT, which is intermediate value theorem, to show that e to the x equals 3 minus 2x on the interval 0 to 1. So what you first do is you make sure that these are all continuous along the interval, and you know that because e to the x is defined between 0 and 1, and x is also, or 3 minus 2x is also defined between 0 and 1. So you kind of know that's continuous. And then you also need to show that that they're not equal at 0 and 1. So what you do is you do e to the 0 equals 3 minus 0. So this side is 3, and this side is 1. So they're not equal. So this is at x equals 0, and this is at x equals 1. We'll do e to the 1 equals 3 minus 2. And that's obviously not true. E, as Addison defined earlier, e is approximately like 2 point something, and you don't have to worry about what it is specifically. And yeah, so the next part is you actually have to show that there's a root that exists. So these are kind of like the preconditions. So you need to show that what is it? Yeah, so you just need to show these preconditions, and then what you need to do after that is you need to move everything to one side. So you get 0 equals 3 minus 2x minus e to the x. And then you kind of set a function. And what you're doing essentially is you're showing, so this will be like some function, I think it'll be like something like this. I'm not sure. And what you want to do is you want to find where this function is equal to 0. And the second condition is, sorry, the second condition, I kind of worded that poorly. Sorry. So our first step is defining a function. This will be our first step. So our first step will be defining a function by moving everything to one side. And what you'll do there is you'll get condition 1, which is showing that it's continuous. And then condition 2 will be, yeah, and condition 2 will be showing that f of 0 does not equal f of 1. Because then this isn't specifically the intermediate value theorem, it's a different thing. And it kind of won't really help us. But so you show that f of 0 isn't equal to f of 1. And you kind of show that by like plugging it in, and you would get 3 minus 0 minus e to the 0 does not equal to 3 minus 2 minus e. And you can kind of understand that this isn't true because e is an irrational number with some decimal, but this side has no decimal, so they're not equal. But if you wanted to fully confirm it, you could just use a calculator and evaluate what these actually are. And so now that we have our function, so I'm going to rewrite it. So f of x is equal to 3 minus 2x minus e to the x. And what you need to do is you need to find, well, okay, so I already evaluated that f of 0 is equal to 2. I think I miswrote it earlier, but so I can rewrite it correctly. So 3 minus 2 times 0 minus e to the 0 is equal to 3 minus 0 minus 1 equal to 2. So Kritik said, can't we just say that since e of 0 is positive and e to the 1 is negative, or sorry, f of 1? I think you mean f of 1. So since f of 0 is positive and f of 1 is negative, there has to be a point in which the line crosses the x-axis, thus proving a root. That is actually exactly what the intermediate value theorem does, but you kind of have to do it. You at least have to do the math for it. And so f of 0, we plugged it in there, and then f of 1 is, like you said, it's negative. We'll get 3 minus 2 minus e. So if you want me to write the ones there, then you get 3 minus 2 minus e, and then you get 1 minus e, which is approximately negative 1.72. And yeah, so like Kritik said in the chat, essentially you would have some point at x equals 1 that's at like negative, and then you'd also have some point at x equals 0 that's like positive, and on the interval, since f is continuous, regardless of how it's shaped, it'll always cross that axis and become 0. I don't know why the whiteboard disappeared again, but yeah, so that's how that one works. You would essentially write those calculations and then say that because there's some point 0, so you would say because there's some point f of 1 is less than or equal to 0 is less than or equal to f of 0, because yeah, like we said, this was 1 and this was 2. Yeah, this was 2 and this was negative 1.72. And because there's some point, like because 0 is between them, then there has to be a root that exists since f is continuous as well. And the next problem is we're going back to limits, but this time these are infinite limits. And what we're doing is, so I'll just write out the limit real quick. Limit as x approaches infinity of t minus t squared root of t over 2t to the 3 halves plus 3t minus 5. And like Addison stated earlier, it's always best to divide by, sorry, this didn't, yeah. So this is t to the 3 halves, and like Addison said, it's always best to divide by its exponent. And this is also something to note. If you see a square root, you probably want to convert that. So this is t times t to the 1 half. And if you know your exponents and like multiplying them, then that will lead to t to the 3 halves. And so 3 halves is the greatest one, both in the numerator and the denominator. And for, yeah, so I'll just rewrite it here, t to the 3 halves over 2t to the 3 halves plus 3t minus 5. And what you want to do is you want to divide by the highest exponent. So in this case, you would do 1 over t to the 3 halves over 1 over t to the 3 halves. And what this does is it cancels out the largest exponent. And that means that things will either become a constant or it'll become some sort of 1 over infinity, which is equal to 0, which is really nice. And you'll see that as we continue. So the limit as x approaches infinity of, and then if we divide t by t to the 3 halves, you get 1 over t to the 1 half. And then if you divide t to the 3 halves by t to the 3 halves, you get 1. And then if you divide 2t to the 3 halves by t to the 3 halves, you get 2. And then if you continue on with this, you get 3 over t to the 1 half. It's a terrible one. Minus 5 over t to the 3 halves. And this will go to 0. This will go to 0. This stays the same because there's no t involved. This will go to 0. And so what you end up with is you end up with 0 minus 1 over 2 plus 0 plus 0. And that gives negative 1 over 2. So that should be our final answer. And the next problem is also derivatives, or not also, it's no longer limits, it's derivatives. And that one is asking for the tangent line at 2, negative 4 for y equals 4x minus 3x squared. And in order to do this, what you need to do is you need to use your definition of the derivative. And in that case, so the derivative at a point specifically. So in that case, we have the limit as x approaches a of f of x minus f of over x minus a. And you just need to memorize this equation. And if you know how to use it, then really the only thing that you have to memorize is just the equation itself. And after that, like you would just use that equation and just it's plug and shove. So the limit as x approaches 2 of, because so x is 2, right? So x is 2. Why did that unshare again? Am I pressing something? Doesn't look like it. Okay, sorry. So we have y equals 4x minus 3x squared. And we also have the point 2, negative 4. And what happens is you get the limit as x approaches a of f of x minus f of a over x minus a. And that's equal to f of x, which is 4x minus 3x squared, minus f of a, which is 4 times negative 4, minus 3 times negative 4 squared, right? Whoops, no, 2. It's 2. Because x is equal to 2, so 4 times 2. And if you plug that in, then you get, this is 8 minus 12, which is equal to negative 4. So what you end up getting is, and then also the bottom is x minus 2, because a is 2. And what you end up getting is the limit as x approaches 2 of 4x minus 3x plus 4 over, because this is negative 4, and then this is also a minus here, so it's minus negative 4. But yeah, and this is x minus 2. And if we factor this, so it might be easier to also rewrite this as negative 3x squared minus 4x minus 4. And in the interest of time, I'm just going to show you what this factors out to be. And this should be 3x plus 2 times x minus 2. And the denominator is still x minus 2. And so notice how those two cancel out again. So we get the limit as x approaches 2 of 8. So 3 times 2 plus 2, which is 8. And then there's also this negative here. So this negative goes there. And we get negative 8. Actually, you shouldn't write that limit there. So this limit goes to negative 8. And we're not done yet. This actually just gives us the slope. So again, that overall limit that I wrote with x minus a f of x minus f of a over x minus a, this is equal to the slope. And we solve that to be negative 8. And so after that, it's as simple as using the point slope formula. So y minus y1 equals m times x minus x1. And y1, in our case, so remember our point was 2, negative 4. So we would have y minus negative 4 equals m times x minus 2. And then y plus 4 equals, I didn't put it in, but negative 8 times x minus 2. And you can write it in this way. If you're more comfortable, you can also just distribute this 8 into both the sides, but you can end with this. And so the next problem is the derivative of a function. Let's see here. So that would be f of x equals 2.5 x squared plus 6x. And if you try to find the derivative of that, you want to use this derivative definition. Over h. And essentially what this is doing is it's actually doing something very similar to our first problem that we did, which is tangent line problem. And it's really just finding points for like really small h, so like h is 0.0001 or something like that. Notice how like when you do a limit as h approaches 0, it like approaches like a certain value. And that's essentially what this equation is doing. And so what we're trying to do is we're trying to evaluate our derivative. So f prime of x is equal to the limit as h approaches 0 of 2.5 times x plus h squared plus 6 times x plus h. So remember this was f of x plus h. And then you subtract off. So I'm just going to put big brackets to like help you see more clearly like what's being separated. 2.5 x squared plus 6x. And this is all over h. So try not to forget that because sometimes people get really busy like evaluating the numerator and they forget about the denominator. And so the next step is expanding the squared. because that's kind of, all the other ones are fine. If you actually, yeah, so you need to distribute as well. So distribute the 6 between the two, and there's not really anything you need to do with that side. But so if we evaluate 2.5 x squared plus 2xh plus h squared plus 6x plus 6h minus 2.5 x squared plus 6x minus 6x, because I distributed this into both of these, all over h. And technically, if the grader is strict, they would want you to keep writing those limits as well. And the next problem is, the next part of this is to kind of just simplify things. And I'm kind of, let's see, just because I'm going to be writing a little bit small. So we would distribute the x squareds, and notice this guy and this guy cancel. And so we can actually just ignore those a little bit. And so we're left with 2.5 times, or 2.5 times, sorry, I can't really use the times symbol since there's an x. So 2.5 times 2xh plus 2.5 h squared plus 6x plus 6h minus 6x. So don't forget this one. And actually these two cancel, so we can actually get rid of those. And we're left with all of this over h. And if you plug in 0 right now, it'll still end up with a 0 in the denominator. But if you notice, we actually have an h here, an h here, and an h here. So we can actually cancel out all the h's, and we'll be left with, I'm going to write it here just so you can see everything all together up top. So the limit as h approaches 0 of, I'm going to divide out the h's, x plus 2.5 h plus 6 over h. No, not over h. It's just that. And if you evaluate that, as h approaches 0, this guy goes to 0, this 6 stays alone, so we're left with 2.5x plus 6. And whoops, okay, so I missed this. So this actually multiplies out. So 2.5 times 2 is 5. So then we actually have a 5x, and this actually becomes 5x as well. So we get 5x plus 6. Sorry about that. But yeah, so the overall process is still the same. And the last part is derivatives. So this question is done. Your final answer would be, okay, that's 5x plus 6. And that would be your final answer. So remember that you would use this equation in order to evaluate your derivative. So the last question is on derivatives, and this is simply using things like power rule, or you guys said that you're not using chain rule, but you would use product rule or quotient rule. So I'm going to write these things up here. So power rule is d dx of x to the n equals n x to the n minus 1. And this works for any n. So n could be a fraction, n could be negative, any of those work. And then the other one is d dx of fg. Why doesn't it let you? Okay. Is equal to f prime g plus f g prime. And you can flip that however you want, as long as you're doing one derivative and then one function and then another function and then the other derivative. So as long as you're making sure that you have both of them exist, because some people are more comfortable with one or the other. And then this is the other one, the last one, f over g, and you get the derivative. Actually, I'll try to write it the way Addison wrote it. I think she wrote it. Never mind, I don't. So this one is very important to make sure that you get the derivative correct, because this negative will actually change things. Because in the case of product rule, the addition, like if you flip them, it's okay because addition like won't have an effect. But if you write the wrong negative, then you'll get g prime minus f prime g, which is not the same. It's actually the negative of what you want. So you have to make sure you're careful of that. But anyway, so the first problem is g squared on the denominator. And the first problem is y equals 1 over square root of x is 1 over the fifth root of x cubed. And the first thing that I do whenever I do these kinds of problems is I convert everything to, it's a not very clear 5, but I convert everything to just power form. So in this case, fractions always have a negative exponent. So it would be, well, x on the bottom would always lead to a negative exponent. And square roots are 1/2, so negative and then 1/2. And then this one is, sometimes it's a little tricky, but I just remember whatever the power is on the x, and then I just do divided by 5. So again, because it's on the denominator, we have a negative number, and then x is cubed, and then because it's a fifth root, we have over 5. And that's what we have for our y. This is still our y. So if we want to find dy dx, then we do our power rule. So it would be this guy. And we would multiply negative 1/2 x to the negative 3/2, because 1/2 minus 1 is, or negative 1/2 minus 1 is equal to negative 3/2. And the other one would be minus negative 3/5 x to the negative 8/5. Notice how I put this in parentheses. I often do this in order to make sure that I don't make as many mistakes with negatives. And then like after that, I would write out like the cancels out of the negatives. And then so that's your final answer for this one. And then the next problem is, let me go ahead and rewrite it. X sine of x minus x sine of x minus x e to the x. This one uses a lot of product rule. And what you usually do is you kind of separate the two, and then you would take the derivative of them, so cosine x, and then 1. And actually oftentimes it would be best to label them. So you would say f prime, f, g, g prime. And when you're doing product rule, you would say f prime g plus g f prime, or as long as everything's there. Sorry, whoops, f g prime. Sorry about that. So f prime g plus f g prime. So f prime is 1 times sine of x plus f, which is x, and then g prime, which is cosine x. And then the second part is doing this one too. So in case you might forget that negative somehow, it might be helpful to do that. So in this case, f equals negative x and f prime equals negative 1. And then g equals e to the x and g prime. Derivative of e to the x is just e to the x. So we're left with that. And so we have plus negative x, sorry, we'll just do it prime first. So negative 1 times e to the x plus negative x times e to the x. And that gives us a final answer of sine of x plus x cosine x minus e to the x minus x e to the x. And that should be our final answer. And the next one is y equals, h of t equals t to the fourth, I'm going to rewrite that, h of t equals t to the fourth minus 1 over t to the fourth plus 1. So whenever you see fractions, you want to do quotient rule, which if we recall is f prime g minus f g prime over g squared. And in order to do that, we again label our f and g. And then we get f prime equals 4t cubed and g prime equals also 4t cubed. And then we plug that in to our equation and we get h prime of t is equal to 4t cubed times t to the 4th minus 1 plus 1, sorry. We're doing f prime times g. And we're subtracting, so remember the subtraction, f times g prime. So t to the 4th minus 1 times 4t cubed. And if you think about the fact that these look very similar, you might just think that like a lot of things will cancel, and they will. So don't forget to write that denominator as well, and don't forget to square it. So if you look at the denominator, or the numerator, if you look at the numerator, you'll see 4t to the 7th plus 4t cubed minus 4t to the 7th. So I'm going to put this in brackets so we don't mix up whether things are plus or minus. So minus 4t to the 7th minus on the inside of the brackets 4t cubed. Now, you might think that these two will cancel, but because this is minus and negative, it'll actually end up with 8t cubed on the numerator because the t to the 7th actually will cancel. So you'll have 4t to the 7th minus 4t to the 7th. And so you get t to the 4th plus 1 squared on the denominator, and that carries on all the way to the end, and you end up with that. So that should be your final answer for that one. And the last question is chain rule. I think some of you said that chain rule won't be on the exam, but we'll just go over this one real quick to make sure that you understand it. And it doesn't hurt to make sure that you understand things ahead of time, even if they're not on the exam. So I'll just go through this one really quick. So the chain rule, so the question is y equals x squared plus x cubed to the 4th, and dy dx is, so when you take the derivative, you have to take the derivative of the inside, and then you also have to take the derivative of the overall thing. And so usually I do like the overall one first. So if you remember your d dx of x to the n, so this is a power rule, then you would do 4 times x squared plus x cubed to the 3rd. But you're not done yet because this inside complicates things. And what you need to do is you need to multiply by the derivative of x squared plus x cubed, which in this case is actually just a series of power rules with 2x, 3x squared. So our final answer would be 4 times x squared plus x cubed times 2x plus 3x squared. And that's your final answer. What topics will be on the exam so I can make sure? I'm not sure the specific topics, but I would like to think that what Addison went over on the PowerPoint should be all the topics that will be covered on the exam. We've linked it, so it'll after we edit through this YouTube video, it'll be posted, and you'll see the recording, and then you'll also see the PowerPoint. So that should be there. I'm not actually sure specifically what's on the exam though, so I don't know if we have everything, but we should have most of the things, at least with the problem-based or most of the conceptual stuff.